The last part of this workshop on estimation, the part 4, is about estimating things that involve sums and integrals. We will not touch about all of these techniques. There are many ways you can estimate things, sums and integrals. It's a very difficult topic, actually, but I want to just say some of the most common things that you do. So if you have a sum of things, some simple estimates that you can do is you can estimate a sum by n times the largest element. So n times m if an are always less than m. And similarly, the easiest lower bound you can often do is you can estimate, the easiest lower bound that you can always do is you can estimate by L times n if for all n natural numbers, an would be bigger than or equal to L. So all n goes 1 through capital N. So this is surprisingly simple, but it's often a useful bound. You've used it in your homework a couple times. Now, there are other things that you can do. You can, if you have an upper bound for each of the terms, for example, you have an upper bound by the absolute value, you can estimate each of the terms individually by the upper bound. And conversely, if you have a lower bound for all the terms, now often the lower bound for these terms is minus the absolute value. So you can actually estimate from below by sum of minus absolute value, an sum. Actually, these two facts are what combine to saying that the absolute value of an is less than or equal to the sum of the absolute value of an's. This is what you call the triangle inequality. Now, similarly, if you have b bigger than a and you're integrating fx dx, the easiest bounds that you have from above are, you give any bound for f of x. So this would be bound of by m times b minus a if f is always less than m. Or in general, you could have an upper bound of any other function that bounds f. And a lower bound would be given by any lower bound. So in this case would be b minus a times L. Other upper bounds for integrals, come from once you give more complicated things. So for example, ab absolute value of f, and a lower bound gives you integral from ab minus absolute value of f. So combining these together gives you the triangle inequality, integral ab absolute value. Steal a little space from here. Gives you integral ab absolute value of f is less than or equal to integral of absolute value of f. So one thing that is worth noting and important is that a lot of the time your sums will be finite. So if you have an infinite sum, you cannot just use these directly, but you have to usually add a few more arguments. So if you want to show an upper bound for an infinite sum, and usually this only applies for positive terms, then what you have to show is actually that all of the partial sums an would be less than or equal to m. This is sufficient. If this is true for all n, then this implies that the infinite sum converges and is less than or equal to m. The issue with these bounds for finitely many indices is that you have to somehow argue the convergence. And this is where the non-negativity kind of comes for free. So I want to give a few examples of this principle. Suppose I have a space of functions, so f, a, b to 0, 1, that are continuous. I define the integration function that integrates f, and b is bigger than a, so we have a positive integral here. I want to show that this function is bounded. That means that there exists an m such that f of x, I of f will be less than or equal to m for all f in x. Well, how do we prove this? So the thing is, we have to estimate. Okay. And how do we estimate? Well, we're looking at I of f. There are the three questions. What do we estimate? We're estimating I of f, which is an integral of the function. How do we estimate it? We are estimating it from above. Let's go to our estimates from above. And we would like to use one of these two things. Let's see, can we use one of them? Well, our function is fortunately bounded from above by 1. So this integral would be bounded from above by integral a b 1 times dx. So maybe first we put the absolute values inside. And then we estimate the absolute values by 1. And that gives us b minus a. And this could be our m. So choose m is equal to b minus a. And then this is function indeed becomes a bounded function. So sometimes the biggest problem is just translating these statements into what needs to be done, and then doing straightforward estimation. Now, as I mentioned, sums can be estimated in very many different ways, and integrals as well. And some of the tools that often are useful are Cauchy-Schwarz. So if you have an absolute value of two things that come as a product of two things, then you want a square in your estimate, then what you can do is you can take the squares of the first square root and take the squares of the second terms and take the square root of that, the product. In general, if you don't want squares, but you want other powers, you can use what is called Holder. So you can put an to the p, 1 over p, and bn to the q, 1 over q, where 1 over p plus 1 over q is equal to 1. The special case of 2 and 2 is these Cauchy-Schwarz. So the first one is called Cauchy-Schwarz, and the second one is called Holder. One of the early week supplementary lectures of this course actually proves these inequalities in a slightly different language. Now, for integrals, you also have similar estimates, and they're proven in very similar fashion. So, and the analogy here is that sums behave like integrals. So if you take an integral of the f squared integral, square root of the integral, and similarly for g squared, and you product them, then this will be an upper bound for that. But in general, you'd have to take absolute value of f to p, 1 over p, ab, and then the same for g, but with a qth power, and with the same condition. These are called dual exponents, by the way. And even in the integral case, this one is called Cauchy-Schwarz, and the second one is called Holder. So you often use these if you have a product form, and if you, for some reason, want a square in your estimates. So one example is, suppose that absolute value of an squared is finite. I want to show that an over n sum converges. This is a 131a fact, really. So there's these three questions that we've seen in this workshop. What to estimate, upper or lower, and what can we use? So what are we estimating? Well, if we want to prove that a thing converges, an easy thing would be to estimate sum of absolute values. So we want to really prove that it's absolutely convergent. So we want to prove a bound for this. But as we said above, this really comes from bounds of partial sums, because now it's a sum of positive terms. And that's why we do the absolute summability. Are we proving upper or lower bounds? Well, we have to prove an upper bound for these partial sums. And what do we know? What can we use? We can use that the sum of squares is finite. And we might already notice that, okay, we might as well think of also the squares of the n squared is finite. Okay, let's estimate. So fix capital N, natural number. Let's look at the sum. N equals 1 to n, an over n. This is less than or equal to, by Cauchy-Schwarz, the sum of an squared, square root, plus sum n equals 1 to n, 1 over n squared, square root. So here we're using an is absolute value of an. So an prime, if I wanted to use different, and bn prime is 1 over n. So that's the product that we have. So this is this times 1 over n, and that gives us these terms here. But this is exactly kind of what we would like, because now each of these terms we can bound from above by making the sums infinity, because we're adding positive terms. This is often a tool that you can use if you have things that are convergent. It's not useful if they don't converge. And this is some number m, which is less than infinity. So for all n, we've got, since n was arbitrary, that the partial sums of absolute value of a and n would be less than m. Now, since the partial sums are bounded and they are non-negative, that the terms are non-negative, we get that by bounded convergence, that the infinite sum is also, that the infinite sum converges. And actually what we get, if we go back to one of these facts about working with infinite sums, is if you can prove some bound for finite sums, you automatically get that bound for infinite sums. So an extra benefit of this proof, even though we didn't really ask for it, we get an estimate. The sum of absolute value of an over n is less than or equal to the infinite sum of an squared, 1 over n, sum n equals 1 to n, 1 over n squared, square root. But there's one more word in this proof. Absolute implies conditional convergence. So the original series, an over n, converges. And because it converges, we can also put here absolute value, the absolute values on the outside. Will not make sense unless it converges. But this concludes the sequence of this workshop. I hope you found it useful. So some things to take out from this last one. 3 steps. These 3 questions are still often useful. You usually need to estimate first finite sums if you are even to estimate infinite sums. Often you use absolute values because with series. And Cauchy-Schwarz is a useful technique. If you don't want to use Cauchy-Schwarz, often there are simpler techniques just by estimating n times the maximum of terms, or by placing the absolute values inside. So triangle inequality. These tools cover most of the estimates that you need, There are lots of more advanced tools that this course doesn't have really the time to touch upon.